Algebra lesson 3-2. We were working on solving equations with addition and subtraction last time. Now we're going to take that one step further and deal with a few other transformations that we might have. So here we have the idea that if you multiply on both sides by the same value, you're transforming the appearance of the equation but not the value of the equation. And the same idea that you can divide on both sides, which again will not change the value but will change the appearance. So these are just some more transformations that we use, the same as adding something to both sides, subtracting something from both sides. That's a transformation, multiplying or dividing on something on both sides. These are all properties of equality. And I put this underlined and I made it bold because it's absolutely crucial. If you forget this step, it will mess up your equation and you won't get the right answer. Properties of equality. Equality really means equal. We have these properties for addition, subtraction, multiplication, and division. What you do to one side of the equal sign, you absolutely must do to the other side of the equal sign. Not the same side. I don't want to see a problem where we have x plus 3 plus 2 equals 7 and someone goes, I'm going to add negative 3 here and here. That's on the same side of the equal sign. That does you no good. You must, whatever you do to one side, you must do to the other side of the equal sign. Just remember that. It has to be done to both. Otherwise, it's not fair. It's not equal. Okay? It's not an equality. We have the idea of what we call similar triangles. This is the symbol right here, making it a little bigger. That's the symbol for similar. And obviously, this is the symbol for triangle. Go figure. So we have similar triangles right here, which would be equal corresponding. Corresponding is just a fancy way of saying matching angles. So if we looked at two triangles, and this one right here being one of them. Oops. Alright, and the other one right here, you'll notice that that triangle fits up in the top. And the reason? Because this triangle, if you're looking at it, get rid of this one, just grab a different one. If I clone this one, I know that this is exactly the same. They fit because I cloned it. But I'm going to make it smaller. And you'll see that it fits right up in there. So according to what we're saying, this angle is exactly the same as that angle, which means it has a corresponding or matching angle. Now this corner down here, it's exactly the same as that one there. And this corner here is exactly the same as that corner there. Even though this triangle is larger, the angles are the same. Remember, we get caught up sometimes thinking, how can this angle be the same size if those lines are longer? Well, an angle measurement is the degree between the sides. It has nothing to do with the length of the sides. If you were to look at the corners of this room, not all the walls are the same length, yet most of them come together and form 90-degree angles. The length of the wall has nothing to do with the fact that it forms a 90-degree angle. So these are corresponding because that one matches there, that one matches there, that one matches there. That's what corresponding means. So even though this is bigger, I would say the two are similar. They have a relationship. Maybe this triangle is twice as big of length than this one is here. I don't know what it would be, but there could be some relationship. So here are some examples where we would use inverse operations, and it would be multiplication or division. So currently, between the negative 3 and the x is a multiplication sign. Well, I want to isolate x. I want to get x completely alone, as I've done in the past, so I must get rid of this negative 3. So here's a really common mistake. People see that and they go, oh, I'll add 3. And then they say x equals 5. Well, you can try that answer out, but negative 3 times a positive 5 does not make 2. So it's clear that that's the wrong answer. What happened? Someone saw the negative 3 and they were thinking addition and subtraction rules, and as a result, they got the wrong answer. Remember, this is multiplication. You have to do the inverse of multiplication. The inverse of multiplication would be to divide. Alright, now another common mistake is somebody says, okay, I've got the division down, but then they want to make this part a positive. That negative 3 and this positive 3, they're not opposites of each other. So, I mean, they are opposites of each other. We want to divide by the exact same value. We want to undo multiplying by negative 3. So we don't want to make this a positive. We want to keep it as a negative. The rule says whatever you do to one side, you must do to the other. So here we have a scenario where there's a negative 3 on top and bottom, which means they cancel out. And x is now alone. And we have a fraction. Now remember, negative 2 on top of 3 is the same as a negative in the middle with a 2 and a 3 is the same as the negative 3 on the bottom. As long as there's only one negative sign, it's the same. So if you want to leave it on the bottom, you can, or you can say negative 2/3. But that would be your answer. Now you can test it. If you did take this answer and plugged it back in, then you'd have this negative 3 being multiplied by negative 2/3. And negative 3 written as a fraction would be negative 3 over 1 multiplied by negative 2/3. A negative times a negative makes a positive, and the 3's cancel, and you're left with 2, which is exactly what we had. So we know that the negative 2/3 is a good answer. It works when we plug it back in. I'm a high bit. I'm really large on trying your answers out and seeing if they work. Okay? Now we have x over 9 is equal to negative 25. This line right here means division. So the opposite of taking something and dividing by 9 is to multiply by 9. So I will multiply by 9. But how do you write 9 as a fraction? You write it as 9 over 1. And whatever you do to one side, you must do to the other. So a question I'm often asked, and sometimes I ask it before anyone else, why did I write it as a fraction on this side, but not write it as a fraction on that side? The reason? This one looks like a fraction. So that's why I wrote it as 9 over 1, so that I could clearly see that the 9's would cancel out, leaving me with x over 1, which is really just x. Over here, the negative 25 didn't look like a fraction, so I had no need to write 9 as a fraction. Had this been a fraction over here, I would have written 9 over 1 as a fraction also. But it's not. So x is alone, and I know a negative times a positive makes a negative, and I have 9 times 25, which is going to give me 225. If it was 25 times 10, it would have been 250. So I know I'm 1 less than that. 125 less than that puts me at negative 225. You can test it. You can plug it in. Negative 225 divided by a positive 9 would give you negative 25. So this is inverse operations. And a final example. People get very confused. They're not sure what to do with this. What you have to remember is between the negative 7/8 and the m is multiplication, which means the opposite of multiplying is to divide. So we know we want to divide by negative 7/8. But we've been practicing for many days now switching all division problems into multiplication, which means instead of dividing, we're going to take this and we're going to turn it into multiplication. But in order to do that, I have to switch this around and I have to make it negative 8 over 7. I have to multiply by the reciprocal. So if I multiply this by the reciprocal and I put 8 over negative 7, because remember it doesn't matter if it's the fraction or the negative signs on top or bottom, it doesn't matter. And I'm going to come over here, I'm going to write this as a fraction and multiply it by 8 over negative 7. Now you'll notice you have an 8 on the top and the bottom and a negative 7 on the top and the bottom, which means I've canceled it out. Multiplying a fraction by its reciprocal will cancel it out. What I do to one side, I must do to the other. Here's a negative fraction being multiplied by a positive fraction, so I already know this answer is going to be negative. 7 goes into itself once and into 14 twice, so I have 8 times 2, which is 16 over negative 1 is equal to m. Well, that's really a negative value, so negative 16 is m. And if you wanted to test it to make sure, you could stick negative 16 right in for m, which means negative 7/8 would multiply by negative 16 over 1, and a negative times a negative will make a positive. We're hoping this makes positive 14, which 8 goes into itself once, into this negative twice. Negative 7 times negative 2 is 14 over 1, which is 14. So I know that answer works when I stick it back in for m. My final answer is negative 16. We talked about similar triangles. Here's an example involving similar triangles. So I'm going to tell you right now that triangle PNM is similar to triangle. Now I'm going to tell you the same order because I want all the corresponding parts of PNM to match up with TSR. Now I know that the P is in the same location as T, that N is in the same location as S, and that M is in the same location as R when I'm comparing these two triangles. I'm looking here and I see that there's an X side. I don't know this one. I know that one side over here is 6, one side on the bigger triangle is 8, and the side over here that is 4. These two are corresponding or matching sides. These two are corresponding or matching sides. And the relationship between the matching sides of the sides I know has to be the same as the relationship between the sides, even though I don't know one of those sides. So we're going to set up a proportion, and we would say line equals line. That's how I like to start off with proportions. And it doesn't matter where you set things up. I typically like to have the variable that we're looking for on top. So decide. Here is where I'm going to put the unknown. Put it on top of one of the sides. Doesn't matter which one, just makes it easier. If you put it up on top on the right, then you got to think about, what does it match up with? What side did it match up with? Well, it matched up with the side over here that was 4. So I'll put the 4 there. Then we have to think, okay, all the information over here was from the smaller triangle. So underneath I should probably put another value from the smaller triangle, which is 6. I don't want to mix and match. I don't want to put the 8 over here, because then I've got the small triangle over a part of the big triangle. I want small over small. We like things in proportions to set up either vertically or horizontally. We don't want them to match up diagonally. If I accidentally put the 6 over here, now a piece of the small triangle matches up with a piece of the small triangle diagonally, which defeats what I really want. So now the 6 is on the small triangle. It corresponds to a part on the big triangle that's 8 centimeters. And from here, we are all set to use our inverse operations. This line right here means divide. The opposite of dividing by 6 is to multiply by 6. So we will multiply this side by 6 over 1. And I'll multiply this side by 6 over 1. Now the 6's cancel out, so x is alone. And if I really think about it on this side, I have some cross simplifying that I can do. I'm going to try to move this over a little bit. There we go. So cross simplifying, I know that 2 will go into 6 3 times, and 2 will go into 8 4 times. Oh, well now I have a 4 over a 4. But I could do the multiplication if I want. I could go 3 times 4 is 12, and 1 times 4 is 4, but I'm still going to have 12 over 4. So since there's a 4 on the top and the bottom, that 4 cancels with that 4, and it leaves me with 3 centimeters. And so I believe that the relationship is that if that's 3 centimeters, it'll match up with something on the larger triangle that's 4 centimeters. If this is 6, it'll match up with something that is 8. And think about it. If that's 3, the relationship is it becomes 4. That's twice as big as 3, which means this would be twice as big, which is 8. So the proportion stays true. If you accidentally put these in the wrong locations, remember diagonally matching up small and big triangles, then it won't come out okay. You want stuff to either match up cross on proportions and vertical when you set up proportions. You do not want them to match up diagonally. You don't want a corresponding part to be matched up diagonally, and you don't want a part on the same triangle to match up diagonally. You want the parts from the same triangle to either be matched up vertically or horizontally. You want the part that it corresponds to match up horizontally or vertically, but never diagonally.